I believe we are recording.
Okay, hopefully we're recording. If not, I have recordings of this session I can share as well. So very briefly introduce myself. Yeah, hi, I'm Bob Pusateri. I have done all kinds of things with both data platform, SQL Server, application architecture. I was previous co-leader of this group for several years back in the day. And probably the best thing you'll find on this slide is my contact information. So if you got a question later, if you're watching the video later and you want to ask me something, find me on Twitter, Blue Sky, you can email me, go to my website, all that good stuff. Okay, what we're going to talk about tonight is we're going to go through the basics of concurrency, whether you're dealing with a database or an operating system or anything else. And then we'll talk about the isolation levels, why they matter, how they're implemented. And we'll finish very briefly with in-memory OLTP. If you would like to follow along, I have these slides and all the demos I'm going to do available on bob.com/readingdirty, and it will take you to GitHub where you can download all that material and follow it along if you would like to. And I will have that link up again. So very briefly, what is concurrency? Right? The ability for some kind of operation to be broken up into multiple, it can run independently and simultaneously. This usually involves accessing or modifying some kind of shared resource at the same time. And this usually works really well until some kind of limiting factor appears, right? You can't have too many people writing to the same thing at the same time. You're going to run into problems. And this is where, initially relational databases really shined because they had the ability to manage this in an effective and coherent way for the most part. So we're going to start with going back to computer science class, really. If anyone here has a degree in computer science, maybe you've heard of the dining philosopher's problem at some point. It's a concurrency problem. It was proposed by a gentleman named Azure Dijkstra. He was Dutch. I don't know how to pronounce it. It's a very famous computer science professor. He won the Turing Award, which is kind of like the Nobel Prize for computer science. There's also an award named after him now as well. But he was teaching in the mid-1950s or so and proposed this problem where you have 5 philosophers, 5 bowls of spaghetti, and 5 forks. And in order to eat, you need to acquire both forks. If you don't have both forks, then you can't eat. But you can only pick up 1 fork at a time. And once you're finished, you have to return both forks to the table. And if a philosopher is not eating, then they are thinking. So this is a very open-ended problem. There's no right or wrong answer, but you have to come up with a way to make sure that every philosopher is able to eat at some point so that they all don't starve. So, of course, problems can arise from this. What if everybody picks up 1 fork? If everybody picks up 1 fork, then nobody can acquire a second fork, so nobody gets to eat. Maybe what if there's a time limit? What if once you acquire 1 fork, you have so long to pick up a second fork, or you have to release the first fork? What if someone never gets to eat at all? This is, quite literally starvation at that point. So we can take and mold this from a philosophical problem into something, a little more concrete with database structure we might be more familiar with. So we still have, of course, a table, but instead of philosophers, we might have users. Instead of bowls of spaghetti, we would actually have, database tables or objects that we're trying to access. And of course, instead of forks, we have locks. Right? So the same idea, we need to acquire the locks necessary to perform whatever operation before some sort of timeout occurs or performance is negatively impacted. And of course, this is a database problem. Money is also a consideration there. Well, be something that matters. So there's different kinds of conflicts that can occur with this. And some are actually defined by ANSI. They're called preventable read phenomena. So the big 3 you may have heard of are dirty reads, non-repeatable reads, and phantom reads. At the bottom there with the asterisk, ANSI specifies which behaviors are allowed at different isolation levels. They don't specify how to implement them. There's also what are called lost updates and deadlocks, which you may or may not be familiar with. But if you've worked in any kind of high concurrency system, you probably encountered a deadlock at some point. Fortunately, now the database has a pretty resilient deadlock manager that can detect and kill deadlocks before they cause a problem. But back in earlier versions of SQL Server, when I got started, SQL Server 7.0 didn't do as great with deadlock. Yeah. So the first is dirty reads, and when we do a dirty read, we're reading data that has not yet been committed. Right? This is a problem. If someone has a change that's still in flight, you generally don't want to see the effects of that change until it's actually committed and made to actually exist. But there's the ability to read these dirty reads, these changes that have not been committed, right? This is very common, right? In SQL, you would use the command with no lock to enable read uncommitted mode. This can let you work or let your queries return faster depending on what the holdup in your queries is, but the trade-off here is the data you're reading may not be correct or may never have been committed by the time you see it. That's the problem with dirty read. There's also non-repeatable reads. This is where you have multiple queries within a transaction that will get different results. This is caused by a different transaction committing something between reads. And if you allow non-repeatable reads, then your results might change within your own transaction, which again may or may not be a problem. And these are all things that can be problems or may not be problems, depending on what your needs are. But you need to be aware that they exist, and the business needs to be aware they exist. Because I've gone in lots of places where the business has no clue that this is a possibility. And then finally, we have phantom reads. These only affect queries with a predicate, so with a where clause, and it's when membership in your result set will change when you have multiple queries using the same predicate in the same transaction, and those return differing results. That's called a phantom read. And we're going to go through demos, and we're going to see what this actually looks like. We're just talking through the basics of this right now. Lost updates, also known as an update conflict. This is where you have simultaneous updates, and I'm not talking about updates that occur right after each other in a very short amount of time. I'm talking literal simultaneous updates where one user's update will overwrite another user's. So it appears as though the first update never happened. SQL Server does not permit lost updates in any isolation levels. Working with that, you don't have to worry about this. And then finally, our old friend, the deadlock, right? This is where you have two or sometimes more than two tasks that are blocking each other. Each one has a lock on some resource and is trying to acquire a lock on another resource and cannot because another process has a lock on the resource it needs, right? This is the deadlock. Everybody's trying to get locks. Nobody can get it. Something has to break this chain, quite literally the deadlock chain, in order to let this occur. So this is where SQL Server deadlock detection will work. It will choose a victim out of all the processes in the chain. Usually it will try to choose the one that has completed the least amount of work. And then once that victim has been killed, it will release its locks, and the other processes should be able to proceed. So there's different ways to address these issues in the database engine. There's both pessimistic and optimistic concurrency. The pessimistic model says conflicts are going to be expected, so we're going to take locks in the database. This is the classic. This has been around since the beginning of relational database. We're going to take locks. We're going to prevent other processes from doing things, and then hopefully allow greater convenience. So the model came to be where you would have readers blocking writers and writers blocking readers. And if you're using SQL Server older than SQL Server 2005, so if you're using 2000 or older, which I really hope you're not. That last place I saw older than 2005 was when I worked in healthcare, and that was not great. But this was the only option available to you. In SQL Server 2005, they did a major rewrite and re-architecture of the database engine and introduced optimistic concurrency as well. This is where we take fewer locks, not none, but fewer, because we're trying to be more optimistic about it. So we're going to say that a conflict is possible, but we consider it to be unlikely. So we're going to use row versioning, structured version store, where we keep track of versions of changes. And hopefully this will allow us to get higher concurrency with less locking. So we'll look at that for a bit later too. So now we talked about this. Are there any questions before we actually get into isolation levels here? Okay. So again, we're going to start with pessimistic and optimistic. In an isolation level in SQL Server or in any relational database that supports this, which are most, will help determine how isolated your transaction is from the effects of any other transaction, right? So there are 4 pessimistic isolation levels. You can see them here, I won't read them. And there's 2 optimistic isolation levels. Read committed is the default, as I call it. It is, if you install SQL Server or spin up an instance in Azure, right out of the box, it will be set in read committed. You can change the default, but you can only change the default to one thing, which is read committed snapshot. Now, if you are spinning up an Azure SQL database, read committed snapshot is set by So that is the default in Azure SQL Database, but in everything else, it is read-committed. But you can change it. If you want to use any of these other isolation levels, you have to specify them explicitly to get them available to you. If you're curious what isolation level your database is using, you don't know. First of all, if you don't know, it's probably read-committed, but if you really aren't sure, you can execute dbcc user options. And then one of the rows that's returned there will tell you the isolation level of that current session. So that current query window, if you're using SQL Server Management Studio or Azure Data Studio, it can vary by session. It's a session level setting, but that is how you find out. If you want to change your isolation level, the syntax for that is set transaction isolation level, and you specify the isolation level you want. This will change all the queries for that current connection. It will not change them for the database or anything else. You can't change the server, but you can change them at the connection level like that. You can also change them at the query level. You can use hints, table hints in particular. In this case, I think that's a terrible word because they're not actually hints. They're requirements when you list them. The database engine will not use any discretion. It will just do it. So for example, if you wanted to query a table in read uncommitted mode, you could use with no lock, and that would apply to only that table. This is on a per table basis. So if your query joins multiple tables together, you would need to specify that for each particular table. And again, this is pessimistic. So we're expecting problems and we're using locks to try to alleviate those problems. And it's the classic locking model. Readers will not block other readers, but everybody else will block everybody. Right? Readers will block writers, writers will block readers, writers will block readers as well. So you have all this blocking and potential for conflict that comes along. So talk about lock modes here real quick. There are lots of different lock modes in any database engine. SQL Server has many of them. They are all extensively documented if you go through the documentation. Here's a selection of lock modes. There are actually more than this now. There's lock, and this is just a table of the different types of locks and whether there's a conflict, which is a C, or a no conflict, which is an N, and I think I is impossible. But to really simplify things, we're just going to talk about two different lock types. We're going to talk about shared locks and exclusive locks to boil it down and make life a little easier. Locking in a database engine operates in a hierarchy. So in SQL Server, there's 4 levels of this. There's a database, a table, a page, and a row. If you were to do a read query, so a select query, and we're just selecting from a table. So you would take a shared lock at the database, which essentially means there's a connection open to the database right now. Hi, I'm connected to the database. I'm doing something in here. Doesn't matter what. Every connection will take a shared lock on the database. You would take at the table and page level, you take this what's called an intent shared lock. And what that means is that there's a shared lock occurring at a lower level than this, in this case, the row. So if we're reading from a table, we're not modifying anything, we're just reading, we're taking a shared lock on the row or rows that we're reading from. We'll have intent locks at the page and the table level and then shared at the database because we're in there. There is a concept called lock escalation, whereby if the locking engine has lots and lots of shared locks, it will try to promote them to a higher level, like turn them into a table lock instead. But we're going to kind of ignore that for purposes of this discussion for simplicity. So this is a read lock, very simple situation showing how locking works at the read level. If we're doing writes, so if we're modifying something, insert, update, delete is a write as well. We still have that shared lock at the database, but now at the table and the page level, we have either an exclusive or intent exclusive lock or an intent update lock, and an exclusive lock or an update lock at the row level. What this means is we of course need exclusive permission on something to change it. That's the only way it'll happen. The update lock was introduced in SQL Server 2008, and it was kind of introduced to help concurrency play a little better in the sandbox, which is why I'll talk about it here. Let's say you're doing a query that updates a lot of rows, like 1 million rows. You're going to need, again, without escalation, you would need 1 million exclusive locks to do this. Now, the problem is it might take a while to get 1 million exclusive locks. There might be other processes that have exclusive locks on rows you need. you'd then have to wait for them. So before the update lock existed, literally your process would start taking exclusive locks wherever it could, and it would sit and block and wait on these other rows to become available to take an exclusive lock on. The problem is all those exclusive locks you already have are being held and blocking everybody else. So that was decided to be not so great. So they introduced this concept of an update lock. So what happens instead now is your process will take update lock on everything. Once it has all the update locks it needs, it will promote them to an exclusive. But while the update locks are being amassed, other operations can still continue. So it doesn't block as much. It just helps your process play better in the sandbox while you're trying to do a modification of some kind. All right. So now that we've gone through the primer of concurrency and locking and how this all kind of works, let's talk about how these isolation levels actually work. So the first one we're going to talk about is called recommitted, also known as no lock. And you'll notice in the upper right-hand corner here, I have this little table. Those are those ANSI specific read phenomena we talked about. So dirty reads, non-repeatable reads, and phantom reads. Notice they're all yes here. That means they can all happen in read uncommitted mode, right? So because we're not taking any locks, or we're taking very few locks, and we're not taking any locks on the rows, things can happen. Like you can read rows multiple times. You could read rows 0 times. And because of this, you can actually return data that was never, ever true. So if you've ever worked somewhere or used anything where they told you to use no lock in your query because it's faster, you can reply and let them know that it's faster and it's also not necessarily accurate. So do they care about the right results or not? And maybe you don't. Maybe you're doing something where you don't need a complete result set, right? If you're working in, I don't know, social media and you're showing replies to a post, if you don't show every single reply every time, probably not the end of the world. If you're working in finance or medicine and you need to know, how many doses of a drug somebody got today, that might be a problem. So I might not use no lock in that case. I'll also point out that no lock applies only to select queries. So you can use no lock in any query, but if it's anything other than a select query, SQL Server is just going to ignore you. There was a bug back in SQL Server 2008 initially that actually could cause index corruption if you used it on a modification query. That's been long as it's been fixed. So if you're using SQL Server 2008 RTM at this point, you kind of deserve all the problems you're going to have. But yes, this is a select query issue only. So to kind of illustrate this with a photo, to show you what a recommitted query would actually look like, it's a time-lapse photo, right? So this time-lapse photo, the shutter was open for a long period of time while someone was breaking in pool there. And because of that, we simultaneously captured the pool balls all nice and wrapped up and flying around the table, right? There was no point in time where this was ever true. This was never happening, but this is what you can get result-wise when you query something in read uncommitted mode in SQL Server. So what we're going to do is,
what are the intent logs? Intent means what exactly?
Say what?
Intent and intent exclusive logs or exclusive logs. What's the difference?
What's the difference between an intent exclusive lock and an exclusive lock? The intent, anything with intent means, if we go back to that slide I had earlier with the hierarchy, intent means that type of lock exists at a lower level in the hierarchy. So if you have an intent exclusive lock on a table, that means there's an exclusive lock somewhere in that table. It's just a placeholder, basically, is what the intent part means. Does that answer your question?
Yeah.
Okay, cool. All right, so some myths about read uncommitted real quick. It's no lock. That means no locks are taken. Wrong. We'll actually see that in a second here. No shared locks are taken when you're reading the data, but other locks are still taken as normal. And if someone says it makes your query faster, this is wrong-ish. If your query had a lot of blocking on select statements, then this will actually address that issue. If your query is slow for any other reason, and there could be, of course, many of those, this is not going to address that. So with this, I'm going to go now 2 screens here. So I'm going to manually do this. Go over here to SQL Server Management Studio. Is that big enough for everybody to read? I hope. Actually, shoot, I didn't start Zoom it. Hang on 1 second. Yeah, this is big. That's lovely. Zoom that program. My bad. Okay, cool. Now I can zoom in. Excellent. All right. So I have a sample database here I'm going to be working with for the demos tonight. And it is a very simple database of zip codes, just a list of all the zip codes in the United States, right? So if I were to use this database and just do a very simple select query, literally see 3 columns, right? We got the zip code, we got the city and the state that the zip code belongs. This data accurate as of a couple months ago when I downloaded this data. So if I wanted to see how many, cities in the United States are named Paris, well, I could do this query and, see there's a Paris, Maine, Virginia, Tennessee, Ohio, Michigan, et cetera. So just some simple data that hopefully everyone can understand and we can kind of play with a little bit. So we're going to play with some dirty reads now. And I'm going to have to set up another session just to run this query. But in this session, I'm going to open a transaction and I'm going to update the entire table and set the city name to Bob. Okay, now I didn't commit this transaction, so it's not committed, but it's an in-flight change. If I were to go to another session and just run, select star from zip codes with no lock, well, it's going to return all these cities are now named Bob, even though this transaction and the other process never committed, right? It's doing the dirty read. It's literally reading something that is in flight from another process at this point, right? And then I could roll back and undo that. If I came back here and ran it again, well, now I get the real answers again because that transaction, once again, never committed. If we want to see what kind of locks are actually taken, I'm going to spin up a extended event session here that is just going to monitor the SQL Server .lock acquired event. So every time a lock gets acquired, it's going to log it into a ring buffer, and we'll be able to see what locks are actually taken. So I'm going to create this session, start it up, and now I'm just going to run select start from zip code with no lock. Boom. Okay. I need to flush this session out so I can actually read the results. And then if you've never dealt with extended events before, it's lovely. It involves a whole bunch of XML parsing to get it to work to read your stuff, which is why people generally don't like it. But here's what we have. So that whole querying that entire table only took 4 locks. And then just the resource type and the lock mode here are probably what we care about the most. So there was once again, there was a shared lock taken on the database. Actually taken 3 times, and there's what's called a schema stability lock, that's a CHS lock there. That basically means I'm reading from this table, don't change this table while I'm reading from it. So that's taken. So you couldn't do something like insert a new column or drop a column or drop the table while it's being read from. That's literally hey, I'm here doing something. But see, none of those shared locks on any rows are taken. There's no intent locks. This is literally all the locks that were taken to execute this query. So there are some locks, but there are not many locks taken, and nothing at the row level occurs when you're querying with no lock in read uncommitted mode. Does that make sense? Mm-hmm. So, okay, so we're gonna go back here now, and we're gonna, just to sum this up, read uncommitted is not a terrible setting. It exists for a reason, but you really need to understand the risks and the consequences and make sure that your business does too, because this can and will affect the accuracy of the results your database gives if you're just using it and don't understand it. So that's read uncommitted. All right. Now we go to read committed, the default isolation. Love me. I got Justin Wilson on here.
I remember that guy.
That was my childhood watching him do Louisiana cooking on TV. That was good times. So this read committed mode comes with a guarantee, and yeah, Justin Wilson used to always say, "I guarantee." So the guarantee here is that the data that you read will be committed. That is the one guarantee you get. So you notice in the upper right hand corner now there is no dirty reads. Right, that's the whole point of read committed. So we get no dirty reads, no other guarantees than that. Okay, and put that out with the arrow there. So the way this works is that we're ensuring that only committed data is being read by locking. So as we're going along the table and we're scanning it, and in my little picture here, every box represents a row. It takes a lock on that row while it's reading it. Now, it only takes a lock on that row while it is reading it. It literally will lock the row, read it, and unlock the row, and then go to the next row and lock that row, read it, and unlock that row. So the locks are held for the duration of reading them, but they are released immediately afterward. So to go back to my picture of the pool table now this changes kind of how our camera works for capturing this data, right? Because we're taking a lock now on something. So if anyone here fancies themselves a photographer, has anyone here ever heard of a swing lens camera before? Probably not. They're kind of rare. It is a camera where literally the lens will pivot from side to side. So I remember they used to do like a whole school picture a lot of my school years where they would bring in this camera that had this lens that would move from side to side. You could take a super wide picture of the class, right? We do this now. We do it with our phones, you know, and now we swing the entire camera instead of the lens, but they had a camera that did this back in the day. Okay, so we'll go to a picture like this, which is taken with a swing lens camera, and this is actually from my high school. This is not my class. They were a few years older than me, but this was a legendary picture from my high school because there was, of course, one student in the group who decided to take advantage of this swing lens camera that was moving. So if I do it there, we got that guy over there who, while the lens was swinging, managed to make it to the other side. He's got that little smirk going on his face too. He knows what's up. But literally, he capitalized on the fact that the lock was transient. The lock was, you know, he could move and move fast enough to get in the picture twice. So that was cool. The exact same thing can happen with our database rows, right? Since we're only locking one thing at a time, since the camera's only looking at a small part of the picture at a time, rows can move while they're not locked. And we can end up with duplicate results or results that don't get shown at all, right? So we're going to demo that one now and show you. So let's go to my read committed script. I'm going to start by restoring a fresh copy of the database. And again, we're going to use read committed mode now. And remember, this is the default mode. If you install SQL Server and don't do anything else, this is what you're going to get. So to make life a little easier on myself, I'm going to create a unique index on the zip code column. And if I run this query here just to say, how big is this table? Okay, this particular index that we created there has 2 levels and the record count in the lower right there. So there's 41,437 rows in this table. We'll need that number in a little bit. So to see what kind of locks are taken, we're going to begin a transaction. We're going to select our zip code from the zip codes. And then we're going to see what kind of locks are currently being held by creating the spit. Okay, and what you're going to see, if we go down here, it says there's only one lock, there's only one row down there, which doesn't really help us, doesn't show much. That's because we need to really record what's going on instead. So we're going to use this extended event method instead, again, like I did before, but we're going to monitor 2 events now. Before we were just looking at this lock acquired event here. Now we're going to look at lock released as well. So we're going to look at all the locks when they're taken and when they're released to kind of get a better idea. So we're going to start this extended event and we're going to select our zip codes. Okay, we selected them. We're going to flush our session out. We're going to query the results here. And what we're going to see, and I'll make it a little bigger. We have all kinds of locks. We did this in read uncommitted mode. We had only 4 rows. Now we have all these rows and we have a whole bunch of things happening here. But if I scroll down a little bit to the meat here, we have lock acquired, shared lock, sorry, page 404, lock released, page 404, lock acquired 405, lock released 405, on and down. So we see literally we're acquiring this lock, we're reading the row, we're releasing the lock. So we actually can look at that through the event chain and see that's actually happening, just to prove to you that I wasn't making that up. Now here's what's really interesting. We can play a game like that picture, like I was telling you about. So if we have 41,437 zip codes, which one is first? Right? If we just order by zip code.
Somewhere in Maine.
It's what?
Somewhere in Maine.
It's actually New York. It's a military base in New York.
Oh, okay.
It is Holtzville, New York, 00501. I looked that up because I was curious too. So that is the first zip code. Now, if we want to see where in the database, where in the actual file this particular record is located, we can do that. We can use a function called sys_fnphysLoc formatter, which will give us the physical location of this row. And this is where, if you're an internals nerd like me, you actually find this stuff interesting. So file page slot. So it's in file 1. Now this database only has 1 file, so that's easy. It's in page 400 slot 0. That is where this record is located in this index. Now, because we're indexed on zip code, if I change the zip code value, it will move the record, right? That's because the index stores the values in order that they are. So if I change 00501 to 99999 and go to the very end, did the row move Well, yes, it did. It went from page 400 slot 0 to page 488 block 221. So that is literally the other end, and as far as the file is concerned of where the zip code went. And then back to 00501, it will resume its previous location in page 400 slot 0 if I zoom in there. So literally what I'm showing you here is that by changing this value, the row is moving in the index. That's what's happening here. This is why they tell people, if you have a clustered index, don't change the cluster key values, because literally these rows have to move, and that can cause all kinds of extra work to happen. Not bad, but something to keep in mind and try to avoid. So what I'm going to do is I'm going to open another window here, and I am going to run a query where I am going to flip these rows back and forth. So I'm going to set 00501 to 99999, and then I'm going to set it back to 00501, and then I'm going to say go 5,000, which means repeat this batch 5,000 times. So I'm going to flip this row back and forth 5,000 times in a different session. Meanwhile, in this session, I'm going to run a query that's going to count 1,000 times how many rows there are in this index while it's moving. So I'm going to start this, and then I'm going to start this, and it's going to take a little bit of time here, just a few seconds usually. Oh, come on, don't make a liar out of me. It shouldn't take very long at all.
Think of those live demos.
Yes, exactly, right. This is why people pre-record their demos sometimes. Yeah, okay, 21 seconds. I would hope it would take a lot of time, but I'll take 21. That's fine. Okay, so we can't remember, we counted 1,000 times. So if we look at what we captured here, we have just literally copies of what happened. So let's sort and group by and see what our results are. Boom. Okay, so remember there were 41,437 rows in this table that we counted. When the data was moving, we overcounted 666 times and we undercounted 327 times. We got the right answer 7 times out of 1,000. Okay, while the data is moving. Now I'll tell you, normally when I run this, it is not that dramatic. Usually you'll get the right answer about 30% of the time. The idea here is if you have a highly concurrent system where data is moving and you're querying it, this is something to be aware of, very aware of in committed mode, because it will allow this to happen. So if you're happy with, getting the right answer 30% of the time, or 0.7% of the time in this case, then by all means continue using read committed. I'm not telling you recommitted is bad. I'm telling you in certain cases it might not give you the right answer. Any questions on that?
So in this particular example, it's
Yes.
you had a clustered index. So if you're not updating the cluster key, or if it's not a clustered index, then this wouldn't have happened.
If you were not updating the cluster key, it would not happen this dramatically at the very least. You still might get result, but everything you get will be committed, but your chances of undercounting or overcounting, yes, drop dramatically. So any other questions about that one? Okay, all right, so we'll move on here to that demo. Sorry, I'm usually smoother with this. So we're going to go to repeatable read next, and repeatable read builds on read committed. Has anyone here ever used repeatable read? If there's any DBAs in the house, nobody ever raises their hand. This is like the, pardon my expression, the redheaded stepchild of the isolation level family. I've never seen anyone use this in all my years of being a DBA and a consultant and everything else. It exists for completeness, but in my opinion, does not have practical use. Is that thunder?
I think.
Yes, sir. That's right when you said it.
Wow, yeah, there we go. I guess I'm getting wet on my watching the train there. Okay, so the guarantee here is if a query is repeated within the same transaction, the records you read the first time will not change. So that's worded very specifically. The records read the first time will not change. So what this means is once a row is read, the locks are held onto for the length of the transaction. Any row that's read, even rows that don't qualify as a result. If it's scanning the table because you have a suboptimal query or don't have an index and it's read, well, guess what? That lock gets held. The locks will not stop additional rows from being added in later queries. And that is called a phantom read, but that's allowed at this level here. So if I was doing a photo, it'd probably be a like a strobe flash. Oh, and I just saw a strobe flash of lightning out there too. So this guy's swinging a tennis racket here, or maybe it's a girl, we can't really tell, but they're swinging the racket no matter what. They strobe the flash a whole bunch of times. It captured like this. It's kind of like locking every time it does that, right? So to show it more graphically, Again, once the row is read, the rows are locked for the duration of that transaction. Okay, on a second scan, new rows may enter. So if you insert new rows into this table and they haven't been read before, well, then they may show up. But the ones that we read the first time are locked. Okay, and we're going to very quickly demo this one. I have a full set of demos for this, but I really don't feel it's necessary to do it because they mostly show the same stuff we saw before. But what we will do is we will query a table with repeatable reads. So the way to do this, just to show you what the looks like, you have to specify either with repeatable read or you have to set isolation level repeatable read. So what I'm going to do here is I am going to begin a transaction and I'm going to select all the cities in Illinois that start with the letter A and do it with repeatable read. Okay, and there's down at the bottom here, there are 71 rows of cities that start with it. And yes, they're repeated if they have multiple zip codes. So, you know, it has 3 zip codes apparently, things like that. Now, because these locks are held for the duration of the transaction, if I just query sysdm tran locks, now instead of seeing only one record, I'm going to see a whole bunch, right? I'm going to see all these. Here are intent shared locks. You'll see it says IS down there for intent shared. And if we go down, eventually we'll get to the shared locks on those particular rows. Only those rows are locked. If we roll back, they'll all be released, but they're held for the duration of the transaction. If I were to play that row switching game again, I will just tell you what happens here is that you'll end up with deadlocks that cannot be resolved, typically is what happens just because of the way the locks are being held onto. But what I will show you is how phantom rows are possible. So here I'm going to once again specify repeatable read. I'm going to do the other way now, set transaction isolation of repeatable read. I'm again going to query all the cities that begin with the letter A. And again, that's 71 rows. Now, all those locks are being held, that transaction's still open. But if I come over here and I insert another row that starts with the letter A, nothing's going to prevent me from doing that, right? And now if I query again in the same transaction, I will get 72 rows. So that phantom row that we created, even though there's locks being held and everything it saw before, it hadn't seen that row before. If there's no lock, I can do that. Okay, that is repeatable read. Again, I have never seen an actual practical use for this. It's just, in my opinion, there for academic completeness. If you've ever used it, I would love to hear why. Finally, we can pull out the big guns in terms of pessimistic isolation, and that is called serializable. And it builds on repeatable read a little more, and it does not allow those phantom reads to happen. So what it's doing is it's saying, if a query is repeated within the same transaction, the results will be the same. Right, that's not before where if we read a row, it's guaranteed to be there again. This is now, the results will be the same. So data we saw previously will not change and no new results will appear, right? We now need to lock data that does not exist. And if you're wondering how that happens, well, you can of course, you can lock the whole table and then nothing can get inserted, but that doesn't play very nicely, right? We're better than the original MySQL engine where that's all it had was a table lock. So we need a better way to do that, but we need to lock this data that doesn't exist, prevent it from being inserted so we can give this guarantee of no phantom reads. And the way we do this is with what are called key range locks. This defines a range of values that other transactions cannot insert a row within. And if you select a row or range that does not exist, well, that gets locked too. Everything has to get locked. So we're literally defining a range even before we've started reading it, and we're locking everything. And we're actually locking one additional row as well. We're locking the first row outside of that to prevent anything from getting added on to the end. So this is how a range lock works. Oh yeah, oops, I didn't mean to do that. So my picture here is this, a posed photo, right? And this is Elvis with Richard Nixon. This is actually the most requested photo from the National Archives. Elvis showed up at the White House. It was in December of, I forget what year, and he wanted to speak to the president, and they got him in later that day, and he asked President Nixon to please deputize him into the war on drugs. And President Nixon did, and then they took this photo. So nice photo there.
He also showed him his gun, or he tried to.
I read about that. Yeah, he brought a gun in or something like that.
Yeah, the bodyguard stopped him.
Yeah. So yeah, good times there. The picture was not released for, I think it was finally released only like 20 years ago or something like that. But anyway, yeah. So there's your weird history for the for the day. So serializable will be like a posed photo. Everything's locked. Nothing's moving. You know, they could probably take this picture multiple times and get it relatively the same each time. Let's go to a demo for this and I'll show you here. All right, so we're doing serializable now. So once again, I'm just going to restore my database. And we're going to look at the row locking behavior now. So I'm going to create a unique index, once again on zip code. I am going to set my isolation level to be serializable. And I am going to open a transaction and select all the zip codes that begin with 1051, right? So at most, there should be 10 zip codes. I think there's actually 8 or 9 here. Let's look. There are actually 8 zip codes, all in New York, that start with 1051. If we were to go query SysDM training locks now, let's see what locks are being held. Remember, this transaction is open. We will see there are actually 9 locks, and the request mode is range. So it's a key range lock. That's how you know it's using serializable. And we had 8 rows, but we have 9 locks because we're actually holding that one lock on a row outside of it to make sure nothing else gets inserted within this range. That is all I have to show you about serialized locking, unless there's any questions.
So I had a quick question. Is this the same kind of logic that you'd see in like Java's serialization, or?
I am not sure.
Oh,
To be
okay.
quite honest with you. I mean, generally, you know, with serialization in general, right? You're trying to take something and make it so that everything occurs in only one order. That's the serial part. They're doing the same here with this type of locking. But I don't know how Java implements it.
Yeah, they do like take data, then convert it to like bytes, and then deconvert it like somewhere else.
Oh, like when you're saving something out to a file, like an object out to a file,
Yeah.
something like that. I mean, I don't know what kind of locking is taken to do that. But,
It depends, but
Okay.
I think there's different functionalities for that.
okay, I guess it's possible. Any other questions?
Yeah, this is a question. Oh, there. From a few panels back.
Okay.
It's on the chat here. Bob, can you please explain the read committed analogy of the swing lens photo and the read uncommitted analogy? I followed the swing lens photo part, but I did not get,
The uncommitted part.
completely follow the read committed and the read uncommitted.
So the idea there with read committed is you're only looking at a small part at a time. Effectively, that's what's locked. So as that lens is moving across, only a small part of that picture is being actually captured onto the negative at that point, which is what I tried to show with that swing lens camera. As far as the uncommitted, that was the time lapse photo of the pool table, and the idea there was that there's both action and lack of action being captured at the same time. So there effectively is no lock. It's open for so long that while things are moving, you will see the artifacts of that, if you will. Hopefully that explains that a little better. If you got further questions about that, feel free to email me and I can explain it better as needed. So now we're leaving pessimistic concurrency land and going to optimistic concurrency land, where we're using row versioning to try to prevent these concurrency conflicts instead of blocks, right? So we're going to use fewer locks. Fewer locks are needed, blocking is reduced. So readers will no longer block writers, writers will no longer block readers, but writers still do block other writers. We do this what's called the version store. The SQL Server, it lives in the TempDB database. And remember, this is optimistic. We're not saying that conflicts are not going to happen, but we're thinking that they're not going to happen, so we're not taking as much action. I have a picture here of a traffic circle. Actually, where I grew up, we had this giant traffic circle in the middle of town. And if you were in high school and you just got your license, you would see how many times you could drive around the circle before the police or other people chased you away. But the idea here is the traffic circles are an optimistic method of traffic control. Instead of having a traffic light, which effectively makes you stop and locks you, you have this circle where everybody yields, and if there's no oncoming traffic, you can just go. Otherwise, you get to deal with the traffic and try to figure out how to merge your way in there, and usually end up yelling or swearing or something like that, depending on how bad traffic is at the moment. So we're using this concept now called row versioning, where we keep a log or a chain of different versions for each row. It's kept in the version store. So every version of a row will have a pointer to the previous version, kind of like a singly linked list. And these versions are stored in the version store for as long as an operation exists that might need them, right? So if you have an open transaction that's open for a long period of time, you might have a lot of versions in your version store. And that was originally one of the big downsides of this is System resources were definitely more constrained in 2005 when this was released than they are now. If you had a really long open transaction, you could fill temp DB and cause problems. Now disks are bigger, and I think generally the awareness is there that you need to be a little bit better about your transaction management. But that was one of the catches initially with this. So just to show you, like graphically, if we have this represents a row, this box, right? So we have a row with 2 column ID and value. So our row ID is 6, our value is 4. That's the current version of the row. The version store would have a pointer back to a previous version of the row where the ID is still 6, but the value was 7. And then, another version beyond that, perhaps, where maybe the value was previously 9. If the ID ever changed, then it would be a different row. We wouldn't care about it. But we're keeping track of the previous values and the time that that value took effect. That's what T is there. So if I do row versioning a little more graphically than that, using my son's toy wooden blocks, maybe we have a table with 3 rows in it, and then the data type would be, wooden block. We have the value of each row at the different times. So if we're looking at the current state of the table with the 3 rows, it would be those 3, right? They have that showing on the right side of the slide just to show you. So it's green ball, blue rectangle, red rectangle. But if I go back to a previous point in time in the version store, so maybe I say, what was the state at t equals 7? Well, at t equals 7, this was the state, right? And if I go further back in time equals 4, well, this was the state. So we have these different, we can reassemble what the state of the table was at any point in time by using this row version store to do that. So the first optimistic isolation level we'll talk about here is called read committed snapshot. And this gives you the same guarantees as read committed, but it gives you an optimistic implementation though. So there's less locking. So there's no locking, but there's less of it. And this is what we call statement level snapshot isolation. So queries that you run will see the most recently committed values as of the beginning of that statement, not the transaction. And that's an important distinction. If I open a transaction and I run 3 different select queries in that transaction, I might get 3 different results based on what is changing in the table at the time. The fact that they're all within the same transaction does not matter. And non-repeatable and phantom reads are possible because again, we're doing the same thing as read committed, but we're guaranteeing no dirty reads, and now we're doing it with less locking because we're using the version store. So if I go back to my example here to show you why this is advantageous to us, again, at time equals 7, this is the state of the table. So if I begin a read query at time equals 7, my select statement is going to see that. Okay, but maybe immediately after, microseconds after I begin my read statement to read this data, something updates this table. This update occurs. Now, normally there'd be a block going on here because I have a shared block, and you wouldn't be able to take an exclusive block if a shared block exists on those rows. But because that block doesn't exist because we're using optimistic concurrency, now this updating process is not blocked. So it's able to succeed. It can update the values. And the statement that's reading, it's looking at the version store now, so it doesn't care. It sees what it started to see at that time it started. So the statement can read the same version it saw before, and an updater is not blocked. We just increased our level of concurrency by using read committed snapshot isolation. To turn read committed snapshot on, you have to alter the database. You actually have to change the database's settings to enable it. This is the syntax you use to do this. This command will block all database activity for a very short period of time. So when I was a consultant and we would come in and we'd see concurrency issues, this was usually step 1 to working on alleviating those, and this probably resolved 95% of the issues. Like it is really good at doing what it does. But to enable it, you do have to block literally everything for a few seconds. So this is usually where we coordinate with the customer and find a good time to do that. If you execute this with no wait, it will prevent blocking and just fail if it's going to be blocked by something. So that's kind of nice. Or if you really want to force it immediately, you can say roll back immediate, and then it'll be a jerk and roll back every other transaction to enable it. But this is something you gotta think about and enable explicitly, unless you're using Azure SQL Database, in which case it's already enabled for you. So we're gonna go back to a demo here, and we're just gonna demo this real quick. Now we're in the home stretch here in these demos. So we're gonna restore our database again, back to a clean copy of what we had before, and now we're going to enable read committed snapshot isolation on this data. boom, which will happen real fast because there's nothing going on here. And what we're going to do is we are going to, well, we can play a couple games here, but in the interest of time, I think what I'm going to do is just play the row moving around game and show you what happens this time. So we're going to go back to what we had before. I'm going to open a new session here. And once again, I'm going to be moving these rows around 5,000 times. I'm only going to do it, I'm only going to count 100 times this time. But I'm going to do this with read committed snapshot enabled. So let's do this and let's do that. I am wrong database. Hang on a second. I screwed myself over by not doing that. I'll make it try to be quick. Okay. Yeah, let's do this. Like. All right. Boom. So now if I boom. Now I only did 100 times out of 1,000, but 100 out of 100 times I got the right answer. Whereas before I got it less, right before less than that. So the fact that we're using the version store and these rows are moving around, it handles that and gets you the right answer every time. So that's kind of what I wanted to show you here. Any questions about recommitted snapshot?
Any reason not to have it?
Any reason not to have it? At this point, honestly, no. I would tell you if you're not using this, you should probably enable it. You know, it used to be the reason people didn't like it was because, you know, big consumer of DB resources, but then, you know, solid state disks came around and hopefully your servers are a little better than whatever you was using in 2005 when this first came out. So that shouldn't be an issue either at this point. Like I said, this was a bread and butter as a consultant. Like you should be enabling this because it's probably going to take care of your issues for you.
I will comment potentially one case
Okay.
where you wouldn't use it.
Okay.
And that would be from a business logic decision.
Mhm.
If the business says, we would rather wait to get the most recent real value of that row than read the old version of that row,
Mhm.
then you may not want to do it in that case. It's rare because one might argue, well, is it ever really a true value? But I've got customers who say, yes, we never roll back transactions. No, it could automatically be rolled back. But if there is a legitimate business case that says, if these two things come in at exactly the same time, we would rather wait for this update to complete and read that updated value than read. It's a rare situation. And there are places that have thought about this and said, gosh, we really need that new data. I'm like, do you really? Because it's not real until it's real. It's just a race condition. What if your select came in a microsecond earlier and got the shared lock before the update? It wouldn't change it, right? And now you're causing contention on your system. But in something that is a very, very like IOLTP system or even an HTAP system that's high transactional and analytical processing, it's something to be aware of. And as long as the business is okay with it, then you roll forward. But you never want to get caught, oh, we did this. Well, now our data's wrong. You know, and then.
Okay, let's do one more. Let's talk about snapshot. And snapshot is serializable, but in optimistic form. And this gives you transaction level snapshot isolation. So before I talked about statement level, or if you have multiple statements within a transaction, they could see different things, and that was okay. The snapshot, the fact that it's in a transaction now matters. The query will see the most recently committed values as of the beginning of that transaction, the first time data is read in it. So saying begin tran is not enough, but the first time you select something, everything else that occurs in that set of queries, we'll see as of that particular point in time. Okay, now to do this, you once again have to make some database level changes. You have to allow snapshot isolation, which basically turns on the version store for this. And then you have to also say you want to use snapshot level isolation. But once you do those two things, you will be using it. Now, an interesting effect of this is you have what's called a snapshot update time. So we'll talk through this real quick here. We have two processes. So process one reads data in a transaction, but does not commit. Now, as I just mentioned, as soon as it reads data within a transaction, it has a snapshot of everything. So anything else it reads from this point will be as of this point in time that that read occurred. Meanwhile, process 2 comes along afterwards and it reads and updates that same data, but also does not commit. So now we have 2 open transactions. Process 1 snapshot that it's looking at, because it read first, never sees process 2's update because it happened afterwards. And again, it's got a snapshot as of that point in time. If process 1 then tries to update that same data that process 2 updated, it's not going to succeed. It's going to get blocked by process 2. And then as soon as process 2 commits, process 1 is going to get killed and actually error out. It's going to return error number 3960, and it's going to say there's a snapshot update conflict. So to show you that in a demo, we're going to go back here and then restore one last time. I promise it's the last time seeing my cruddy demos here. We're going to allow snapshot isolation. Enable the data
master database.
What? I just said it's a code data, so we're not gonna.
Oh, okay.
Yeah, so it's not gonna affect it. We're going to enable snapshot isolation here, and in this session, we're going to. Again, I'm playing games here with this. I will spare you that, but I'm gonna go down here to the update conflict and show you that instead. So I'm going to begin a transaction, and I'm going to select something. Okay, boom. I selected a row in a transaction. In another session, I'm going to do a couple things. I am also going to enable snapshot isolation in this session because I have to turn it on here. I'm going to begin a transaction and I'm going to update that same row. And that update is going to succeed, 1 row affected. Okay, so we have 2 open transactions. This one just did an update. This one merely queried that row. Now, in this session, the first one, if I try to do this update, it's going to wait. Right, as you see, we're a little executing query thing spinning down in the corner there. It is actively blocked and waiting. If in this session now I commit, because this is where the change actually took place, this will commit just fine, and this one will get killed. All right, snapshot isolation transaction aborted due to update conflict, blah, 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 error 3960. So this can occur with snapshot isolation. This is just a effect of actually reading a snapshot, and changes can occur in other transactions while that snapshot is going on. Any questions about that? This is something I have never personally observed in the wild, but it did happen. So I mentioned this before, but everything I've covered here works the same way in Azure SQL Database for the same engine and SQL Managed Instance and SQL and Virtual Machine and everything else. The difference is in Azure SQL Database, read committed snapshot is enabled by default. And very, very briefly, I'm going to throw everything out the window and explain in-memory OLTP in like 2 slides. Okay, this creates what are called memory optimized tables, and this could be its own presentation. And other people have presented this by themselves, for an hour at the time. But this is using optimistic multi-version concurrency control. This has no locks, not even for data modification. There are never locks. There's never any waiting for blocking because there's never any locks to cause blocking. There's no latches. There's no spin locks. Sometimes waits can occur because you're waiting on something like writing to disk, but there is no actual blocking that can occur within the data structures. That's because no existing row is ever modified. So anytime you do any kind of update operation, you create a new version of that row. You just end up with this massive ledger of row versions, kind of like what Jared was mentioning earlier when talking there. There may be multiple versions of a row in play at once, depending on what your transaction is allowed to see. So when your transaction runs, when you're reading from the data, you're presented with the correct version based on the time that you were trying to do something. So very briefly, I have a table here. I have 2 rows in this table, and there's 2 columns. There's the data columns there's a number and a color. So we have 1 red and 3 green. And a memory optimized table will also append some other columns. It'll append a beginning time and an ending time to that. So at time 10, we inserted those rows. Now let's say at time 20, we're going to do some operations. We're going to delete the 1 red. We're going to update 3 green to 3 blue, and we're going to insert 6 pink. What's going to happen here is deleting red is going to give it an end time. End time is at time 20, right? So that row didn't disappear. It wasn't deleted. It just modified with an ending time. Now, similarly, the 3 green row is given an ending time, and a new row is created for 3 blue that begins at time 20. And then same thing, row 6 pink begins at time 20. So when a query comes along and tries to read now, the engine is going to say, well, what time did this query start at? Did it start at before or after time 20. If it started before time 20, well, it's going to see the rows that existed at whatever time before 20. It started after time 20, well, it's going to be presented with these rows instead. And that is how you achieve everything we just talked about with no logical blocking. Again, world's shortest explanation of in-memory OLTP. There you go. If you're curious about the concurrency and want to learn more and thought this was interesting, Craig Friedman at Microsoft has some great blog posts. Caitlin Delaney at Simple Talk wrote an entire book on it, which is very, very good, published by Redgate. And Klaus Aschenbrenner out in Austria, a good friend of the data community, has an excellent set of blog posts as well about some misconceptions about transaction isolation levels. Once again, if you have any questions and we don't address them here, feel free to reach out to me. And if you're looking for everything you just saw tonight, you can go to that address and get the materials there. Are there any other questions?
But there's a question, I thought I saw somebody with their hand up in the back.
No? Okay.
I might have been fanning myself off.
Oh, yeah.
All right, well, in that case, thank you all for sitting through that. I hope you might have found it interesting, maybe picked up something that will help you at some point though.
Okay. The next month, the March, our next meeting will be March the 14th. And we'll have Jared Posh be doing a presentation on kind of hand folds into this one on deleting millions of rows. So thank you, everybody, for attending, and hopefully we'll see you next month.
Yeah, very good.
This is